Well, good afternoon, everybody. Thank you for attending this session, this expert panel on industrial valves for hydrogen, today's challenges and tomorrow's solutions. I have the privilege of being the moderator of this event. My name is Gil Perez. I've been in the valve industry for a little over 25 years, working for a major manufacturer of valves, more than one in fact, and I have, again, they say the honor, the privilege of sort of moderating this group of specialists, of experts with over 370 years of combined experience. So if we don't have the answer, it's probably a hard question to answer. But even if we don't have the answer, we'll talk about the issues and share our thoughts on that. And from that, hopefully there will be some learning as well. And I just wanted to make sure that everybody understood that we're not necessarily going to be able to answer all the tough questions, because it's a very deep and complex field, very broad, very deep. But we will try to address some of the common themes that are of concern to this industry and this application, as broad as it is. We have with us a total of, including myself, 10 panelists. There's Ray Bishop. I'm going to let them introduce themselves, by the way. There's Ray Bishop, Martin Burgess, Jonathan Galanes, Fadil Khalfawi, Ron Merrick, myself, Federico Ricotti, Pierangelo Scalia. There's Thomas Whitty, who is on the video, but not yet for some reason. And there's Wojciech, sorry, my bad. And there's Wojciech Zmuzinski, who is also part of our panel. I will allow them to introduce themselves, but I'll start with myself. As I mentioned, 25 years in the valve industry. I worked for a manufacturer called Velan. I currently am involved with a company called OMB. My background is as a mechanical engineer, educated in Canada at McGill University. I've got a Bachelor of Mechanical Engineering degree and an MBA, and I've worked in various technical and commercial roles throughout my life in operational and executive management roles. I come to this from a general valve background, and I have most recently been involved in chairing the task group that wrote the recently published standard on testing of hydrogen of valves in cryogenic hydrogen service, on which I will present a summary of that actual standard practice at the end of this program. This program will begin with about an hour and a half of panel discussion, depending on the momentum and energy that we have. We'll take a minor break. We'll then come back and start the presentations. There will be one on a very interesting subject on metallurgy, and then closing with the presentation that I'll be making on the valve testing. And then at the very end of it all, we'll allow Q&A to happen. Also be aware that throughout the first part of the program, which is going to be a more or less a somewhat structured Q&A, we will also allow anybody to raise their hands and ask questions as they wish. So we'll try our best to respond to questions as they come from the floor. So feel free, if there's something you feel is relevant to the subject being discussed, feel free to raise it. Either contribute to it or ask your questions. We'll keep the discussion going as energetically as we can. And poor joke, dad joke, it's hydrogen, so we're going to try and keep it light. So basically, that's our approach for today, and I'm going to now allow my co-panelists to introduce themselves over the next few minutes. So please go ahead.
Thank you, Gil. Is on? Yeah. Can you hear me? Technology should pass, but the moment is not.
King.
Okay. Okay. Yeah. Good. Good afternoon, everyone. This is Federico Ricotti. I'm from SLB Valve. I'm probably the youngest inside the panelists. You know, I cannot ask age of a lady, but probably I'm the youngest, so not contributing too much to the total amount of years of experience, but I'm in the oil and gas industry since 18 years. I'm involved in the designing of 6D, 6A, and 6D SS valve on Grove facility, which is in Voghera, Italy. And I'm considered probably a subject matter expert for new energy, hydrogen, carbon capture, ammonia, geothermal, and so on. So good to have such a amount of people listening to us today. Hope we can reply to all the questions. If not, in any case, it will be food for thought for the future. I will leave.
Thank you. Good afternoon to everybody. My name is Pierangelo Scaglia. I am the Vice President Engineering of MVB Group. My experience is a little bit longer than Federico, and I started to work in the valve for pipeline, casually, always in Grove, and I moved during my 38 years working job through the valve for pipeline, wellhead and Christmas trees, upstream, downstream, and in the last 15 years, I'm not fully dedicated, but a good part of my time is dedicated to cryogenic valves, up to liquid hydrogen valves. That is all. Thank you again.
Good afternoon, everyone. My name is Fadila Kalfawi. I am a corporate metallurgist at VALVE. I do have almost 3 decades in materials engineering and metallurgy, and almost 1 decade in valve industry. I had a privilege when I started at VALVE to work directly with Gil Perez and on challenging subjects. And one of them is, guess what? Hydrogen sulfide. So at VALVE, I am a SME, material selections and coatings. And currently I'm leading several R&D projects in emerging technologies. One of them is in hydrogen. And thank you very much for joining this round table.
Yeah, good afternoon. So my name is Wojciech Żmudziński. I work for BP, based in Houston. My total number of years is about 32-ish. I've started actually as a valve designer in a very small company in Canada, just outside of Toronto, which was then purchased by VALVE. So I knew Gil from those days. So I worked in Montreal for some time. Then we escaped and we moved to Australia. But on the way, I was told by my new manager, why don't you stop in Italy for a couple of weeks, which actually turned into closely to 2 years working on projects in Qatar and Saudi Aramco as well. So that was EPC, valve manufacturing EPC for about combined 11 years. And eventually in Australia, working for SCOR Pacific, also working other industries, not just oil and gas. And then finally again back to McDermott, back to Dubai, and now in BP for about 8 years. So my role is as a engineering advisor. I own and responsible for valve specs for BP, external representation, support to projects, support to operations, and everything else in between that is interesting.
Good afternoon, everybody. My name is Jonathan Gelijns. I'm from SLB, previously known as Schlumberger, but also in terms of valves, maybe better known as Cameron. So Cameron Valve, that was acquired by Schlumberger a couple of years ago. 33 years of experience always with valves. And in the past, like most of you, it's mainly for the oil and the gas business, but recently more on the new energy transition, so hydrogen, but also CO2, geothermal, nuclear, data centers, believe it or not. So all kind of new applications, kind of. So in my role, I'm responsible making sure that we've got the right technologies and materials available, the right valves available for all those new applications. I'm also co-chairman of the API 6D Annex M, so the valve for hydrogen standard. So that was developed a couple of years back and was published 2 years back right now, and it's up and running. So, thank you.
My name is Ron Merrick. I was hired by Fluor as a piping engineer in 1975. So I've got cumulative 50 years of piping and valve experience. So I did project work for years, building line classes, building valve descriptions. I became the corporate catalog maintainer for a number of years, and although I'm retired, I haven't quit working for Fluor. And I do have certainly a lot of experience with high temperature and high pressure hydrogen. You know, the cryo side is, we are going where no one has gone before. So that's been an interesting journey. Thank you.
Good afternoon. My name's Ray Bishop. Work for CB&I. We're an EPC company that does, our main focus is low temp and cryogenic storage. With CB&I, I'm a mechanical engineer with 34 years of experience with them. Again, as a piping engineering manager, dealing with all and the full ramifications from piping design, valve procurement, and onto construction. Like I said, we deal with a lot of storage, low temp cryogenic storage, including hydrogen. And in hydrogen, we've seen an uptake 2 years ago, especially in the FEED studies for hydrogen facilities. It's kind of tailored off, in the past few years, but hopefully it'll come back to us.
Good afternoon, everyone. I'm Martin Burgess. I'm the engineering manager for SCORE Europe in the UK and also the Valve SME. My background is mechanical engineering, so I'm a chartered mechanical engineer, and I've worked in the valve industry ever since I left school, so at 16, so that's over 25 years as well. My expertise is mainly in isolation valves, so valve design, repair, maintenance, failure investigation. More recently, we've been working with hydrogen and some national transmission system operators looking at the potential repurposing and change over to hydrogen, so introducing hydrogen into natural gas as a blend, or the eventual change to 100% hydrogen. So hope to add to the discussion.
And last but certainly not least, Tom Whitty.
Good afternoon. Can you hear me all right?
Perfect, thanks.
Okay, thank you. I've been in the industrial gas business my whole career, so I started working with Air Products after getting out of school with a chemical engineering degree in the early 80s. I'm mainly a systems engineer, so designing an end-use application. So I've been designing systems, cryo systems, for 40 plus years. Also ran a hydrogen transfill for about 10 years. I had a special project that was very interesting at Cape Canaveral, where we pressure tested the Boeing Delta IV rockets fuel lines, the oxygen and the hydrogen, cold, and some of them were warm, obviously. But it was interesting to see the bigger valves results. I'm currently on the hydrogen safety panel for the Department of Energy, and that's almost all hydrogen, obviously. And do a lot of training, global procedures, but mainly it's end-use applications. So I'm not a valve expert except in using them. Thank you.
Thank you all very much. Very interesting, and you can see what I mean by pretty deep. We've got a pretty deep bench here, as they say in baseball, if you get the analogy. As I mentioned, 370 years of collective experience, an average of 37 years per person. And this summarizes, I believe, yes, you see it. This summarizes the overall, let's say, portfolio of skills and backgrounds we have: valve design and engineering, cryogenic, hydrogen service naturally, piping materials and specs, materials engineering and metallurgy, industrial codes and standards, energy transition, failure investigation and reliability, R&D, innovation and development and patents, engineering, management, and leadership, and technical authorship and training, to name a few. I mean, this is just a synopsis, a collection of all of the CVs of the people in front of you. And so with that in mind, we've put together over the last several months, as working as a panel, we prepared by identifying certain themes, and in each of those themes we're going to proceed by asking ourselves a number of questions. We'll make sure to go through each of these themes at least with one or two, maybe more questions, time permitting, We have 8 in all, and we have several questions per theme. We hopefully will get through all of them, but we may not. Depends on how the tempo goes. I just want to recap what those themes are, or summarize what those themes are. We're going to be talking about metallurgy and material selection. We'll be talking about design and standards, valve technology and selection, corrosion and environmental compatibility, which does certainly connect back to metallurgy, testing, qualification, and commissioning, pipeline repurposing and conversion, fluid flow and systems design, and lastly, maintenance, repair, and inspection. So those are the subjects we'll be talking about, and basically at this point I'm going to turn off that part and we'll begin the Q&A. You know what? Yeah, that was it. So the first theme, as I mentioned, is metallurgy and material selection. And here's the question, and I'm going to open it to the floor. What are the hydrogen damage and failure mechanisms, such as embrittlement, hydrogen attack, permeation, across gas versus liquid services, varying pressures and temperatures, and pure versus compound hydrogen streams? And a sub-question to that is, how does hydrogen embrittlement differ across cryogenic, ambient, and high-temperature services? It's a metallurgical question, it's a materials question, but we each have our perspectives on it. Please, I think, I don't want to put anyone on the spot, but please go ahead and pitch in. And this is going to go, the mic's going to go around to as many people as have some input on this. We may bounce back and forth on each other. If there's a question that comes up during this conversation, please raise your hand and we'll try and address it.
So the failure damage and mechanism vary depending on hydrogen state, whether it's gas or liquid, operating conditions, and composition. In gaseous hydrogen service, the dominant failure mechanisms are typically hydrogen diffusion-driven embrittlement, hydrogen-assisted fatigue, and permeation. At the micro scale, hydrogen tends to accumulate at microstructure defects. Mechanisms such as hydrogen-enhanced localized plasticity and hydrogen-enhanced decohesion mechanisms become active at the high stress conditions. So in practice, there is a delayed cracking, reduced ductility, and accelerated fatigue stress cracking during the cyclic loading conditions. In the liquid hydrogen, the dominant mechanisms shift from a typical diffusion-driven embrittlement to a cryogenic mechanical behavior. So at minus 253 degrees Celsius, the hydrogen diffusion is significantly reduced. So the primary concern is the loss of fracture toughness and the increasing susceptibility to a brittle fracture. So it's two different mechanisms. At high temperature or elevated temperatures, what we see is high temperature hydrogen attack, and basically hydrogen reacts with the carbon in steels, leading to a decarbonization, internal fissuring, and progressive loss of mechanical integrity. Composition. A pure hydrogen behaves differently from industrial hydrogen containing impurities. We are talking about impurities here, such as a sulfur or carbon dioxide. And these impurities can significantly influence the corrosion and cracking acceleration. So basically, there is not only mechanism, but there are several mechanisms of embrittlement depending on the hydrogen conditions.
Thank you. Anybody else have a contribution and feel comfortable about adding?
I would like to add, everything said is correct. We can say that the first attack of hydrogen is decarbonization of the inner surface, the wetted area. For sure, hydrogen is very affiliated with carbon, so hydrogen eat the carbon steel, but the initial decarbonization is not so critical like what is happening later. So hydrogen diffuse inside the material, attack the border of the grains, and create, of course, embrittlement. Then there is also a formation of methane inside the material that can create some defect, some cavities that can generate and can result later in fracture, in cracks. Then, of course, hydrogen is related to stress. The stress level inside the component, inside the valve, the pipeline, the flanges is very important because more the stress, more the hydrogen attack. I would like to invite all the person to, for example, read API RP 941. RP means recommended practice. These recommended practice from API contain, I think, a lot of interesting matters and explanation how the hydrogen attack. We can say that for majority of carbon steel pipeline, there is nothing strange below such temperature that is critical. And according to API, the critical temperature is 400 F, means 204 C. I'm converting imperial metrics for benefit of all. When increasing the temperature, hydrogen became more and more critical because of temperature related and stress related. So the crack propagation in hydrogen related to stress have to be taken into consideration. So fatigue and cycling load on component, piping, valves, flanges have to review carefully.
Thank you. Does anyone have anything they feel could amplify? Tom, you're remote, so I'm going to pick on you a little bit without trying to impose on you. Is there anything you think you want to add? Just making sure.
Yeah, I'll add a few things. Typically, as was indicated earlier, stress is a big issue, and high strength materials are a problem, more susceptible to the hydrogen stress, corrosion cracking, or hydrogen embrittlement. Typically, the industry uses 316 or 316L, austenitic stainless steel. Martensitic stainless steel is not recommended at all for hydrogen embrittlement. So those are the typical materials, and as well, they're also the typical materials used for liquid hydrogen because of its low temperature properties. Carbon steel is not allowed at all for cold temperatures. Usually we have shutdown set at -20. Sometimes you get it down to -50 if you do your Sharpie impact testing of your carbon steel. But typically, it's stainless steel for all these applications. Thank you.
Thanks very much, Tom.
Tom introduced the liquid hydrogen. I would like only add to follow Fadila information that, okay, for liquid hydrogen, the material are very simple because are almost the same, 316, 316L. The most important thing on this material is to verify always not only the rupture, the yield strength, but to perform the Sharpie test and the lateral expansion. The lateral expansion is extremely important because there are some indication on B31.3, okay, around the minimum lateral expansion will be 0.53 millimeter, okay? But this is very important, not for 316 or 316L, 304, but for other materials that in the valve manufacturer use very used to find in the valve manufacturer, like nitrogen, nitronic 50, nitronic 50 mainly. Nitronic 50 that we can find commonly in the valve, maybe ball valve, is called, generally speaking, HS, high strength or super high strength. These materials are not able to pass the test, the expansion test. Okay, it's possible to use the XM19 So the base material, solvilage that you can find in STM. That is good because if you perform the HRP test with more than 50 joules, in low temperature, in this condition, not in low temperature, in ambient temperature, in this condition is probably you have more possibility that is good also in liquid hydrogen application at minus 252. This is very important because it's not true that I take the nitrogen 50, I put, nitronic 50, I put in the valve and this is good because at minus 96 is good. No, this is not true. It's necessary to perform all the tests to verify this. Vice versa for 316, 316L, it's not a big problem. It's also nitrogen 60, but nitrogen 60, nitronic 60 is not approved as l'MR 75. NACE is not NACE. Oh, yeah. Okay, so nice, yeah. When you have hydrogen in gas phase, sour gas. It's not exactly.
Okay. Gil, just wanted to maybe not contribute to the answer, but challenge this a little bit. So the question or the challenge we often see with end users, I work for BP, is what is so unique and different with the hydrogen applications, hydrogen services that we're talking about now, and we haven't seen this in refineries for the last decades, right? Why are we making such a big fuss about this now? And it's there was always these two camps. Well, refiners, very comfortable, hydrogen used, for a long time. What is so different, right? Yeah. And maybe this is something we can get into in some of the other themes, but just keep that in mind. This isn't something completely new. No one understands, and we're testing things, so we don't understand how things fail. There's a lot of knowledge and history and evidence.
Right. I think, and that's the challenging part. I mean, let's be clear. Hydrogen, as I mentioned earlier, as a medium or as a fuel, is applied in many different ways throughout all states, from liquid to gas, at cryogenic temperatures, at elevated temperatures, and at what we would call ambient temperatures. There are many different colors and types and applications that involve hydrogen. Many of them have a long history of use and successful and safe use. Just the same though, API 60 just came out with Annex M and imposed additional requirements for a very traditional application to basically focus on the quality requirements and design requirements pertaining specifically to hydrogen, even though it has been around for decades as an industrial application. So to your point, even where it's known or it's got a long history of use, there's still areas of development and learning that can be achieved. And in the cryogenic domain, it's even perhaps more acute because although yes, hydrogen has been in use for decades as well in aerospace and so on, there is still certain things that are not well established, and I'll talk about that later in the testing piece, that we have to be aware of and sensitive to in finding our solutions. So great. I'm going to move on to another theme because I think we spent a bit of time on metallurgy and materials. I'll come back to it later though, because I think we have not covered it all. I hope everybody can hear me okay. Okay, the next theme is design and standards, and the first question I have on that is, what are the key differences between B3112 and B31.3 for hydrogen piping design, and when should each be applied? And along with that is, what is the future of B3112, and how will its content be redistributed into B31.3 and B31.8? So I'm going to put this out to
maybe I can give a
shot at that. There are a couple of us that know nothing about it, and there are a couple of us who know a lot about it.
So I am a task group member of the European section of the SMA B31.12. So I know a little bit about it, although not globally. So the plan is that all the requirements, so now one step back. So there's the SMA B31.3, which is about piping. There's the SMA B31.8, which is about pipelines. Then there's the SMA B31.12 that specifically talks about hydrogen. So it was difficult to have different standards because if you look about piping, you need to look at B61.31.3, but also the 31.12. So the decision was taken to take all the requirements from that standard and integrate them back into both the SMA B31.3 for the piping and B31.8 for the pipelines. So there is already a chapter about CO2, and then right now they want to add another chapter for the hydrogen. As far as I'm aware, the B31.3, the ballot is being approved right now, so it's pretty close to getting published. The aim is to publish it before the end of the year. The same aim is there for B31.8, but I believe there's a little bit delay in that, but the aim is still there, so it will be published very, very shortly. Then during a period of 3 years, all three standards will coexist. And then by 2030, the B31.12 will disappear and all the requirements will be embedded in the other two standards. So that's about what I know about it.
No, you know a fair bit about it.
Yes. And then I talked to the co-chairs of B3112. Standards making is notoriously dependent on what happens next. So that's the current plan. One of the reasons they're wanting to do this is because it's just too cumbersome to have very similar applications overlapping under the jurisdiction of people who meet at different times and with different constituents. So that seems to be the driver behind all this. Standards making has a tendency to be self-perpetuating, so I'm not holding my breath, but that's what they told me, is that is the plan, and it is actively working, but of course it has to be balloted section by section, paragraph by paragraph, basically. So, you know, it's not surprising that it would take another 5 years or so for that.
So as far as the differences between 31.3 and 31.12, 31.12 focuses on reducing the stresses for the carbon steels especially. You know, the higher strength and the higher hardness steels, we even have a higher derating factor. It's like the material performance factor, I believe. So in reality, the everyday carbon steels are generally safer for hydrogen service because of the brittleness and the lower strength. 31.12 also, you know, has higher NDE. The higher pressures you have, i.e. more stress, the higher NDE percentages you need to do. It has 31.12 for hydrogen has a preheat requirement that 31.3 does not. And also a Bernal hardness check for welding, production welds. So it's, like I said, overall, it's an attempt to assure that the stresses in the carbon steels, especially, are kept low, you know, for the stress corrosion cracking.
I do have another comment, and that is, I have a colleague who actually did a project under B3112, and one of the things that we saw was, you know, and I've worked in different codes, under different codes now and then, and you are kind of at a, you know, you're out to sea sometimes in a different code. Some of the things you're used to doing are just either not done or much more complex. So I think from a practical matter, you know, we get paid to do stuff that's messy, but the closer you are to your comfort zone, I think the less likely you are to screw up, for lack of a better term.
I just want to add one thing. The difference in B3112, the heat treatment, post-well heat treatment, is mandatory regardless the thickness.
I don't know, but what is the general opinion, but the 31.12 is generally considered very conservative in terms of what is the requirement. For sure, post-welded treatment is very important point, because if not relaxing the tension inside the metal, everything that can be scary became very scary. But the material grade is important. I think that while talking about standard natural gas or other application like oil or even H2S, we were always looking at all the mechanical property of the carbon steel, not only for pipeline but also valve, but looking mainly on yield, tensile, impact, Sharpie test. Now we have to look I think at others parameter like lateral expansion, but also reduction in area, elongation, because all the material that are ductile are to be preferred. And we know that welding, so pipeline is not only pipe, is also flanges, connection, where welding are to connect the counter flanges to the pipeline. But we have also other point welded like tapping ports, very minimal mass, but to be checked, because there you can have a residual stress that can be dangerous when you have hydrogen, in addition to something that we have considered in the past not significant, like localized load, variation of geometry, if there is hedges, or other things that in the past were not important, nowadays can be important, because I said before, concentration of stresses, a localized area where the stress have a peak is to be considered. Okay, everyone doing FEA analysis or calculation are trying to exclude the peak stress caused by the geometry, like an edge, because not significant, caused by the calculation algorithm, but now all the single variation in geometry, shape, corners, edges have to be considered, especially if we are going with material above grade X52. I don't know if common X72, 52 can be borderline between milled material and high strength material for pipeline, like for the valve. And so I think this is to be said.
Perfect, thank you. Tom, again, not picking on you, just making sure we don't leave you out of the conversation, with a focus on the cryogenic side and the gases you're familiar with, and hydrogen, of course. Are there any insights, not necessarily regarding ASME, but in terms of design standards or specifications that are relevant and of concern?
Yeah, there is. I wanted to bring up that cast for hydrogen is not allowed in NFPA2. It's not in, I didn't see it in NCB 3112, but they do require permeation testing. But within NFPA2, cast valves are not allowed. For cryogenic liquids, again, it's almost always stainless, although aluminum can be used, but aluminum has such a low melting point, it can be an issue. The other thing that was brought up earlier about expansion contraction in these valves, ball valves are a problem as they get larger, and they're a problem sealing anyway at cryogenic temperatures because of the moisture that can form on it, and also because of the large expansion contraction that's going on. So ball valves are typically smaller if they're going to be used. When I was at Cape Canaveral doing some testing, we had a large problem with a 4-inch ball valve. The expansion contraction was such that the ball valve would never seal at pressure. That was problematic. And I just want to bring up mainly, though, that NFPA2 has some other issues or not allowed materials that are not in ANSI B3112. Thank you.
That's good insight, thank you. Okay, I'll move on to the next theme. The next theme is valve technology and selection. And I might pick more than one question because we have quite a few here. What is the manufacturer's current technology readiness level? And what validation and qualification pathway, including 6D, Annex M, QL, SLH criteria, is required? This is very targeted, and I think there are a couple of specialists who can add some insight to that question.
You can take it over later, Federico. So yeah, well, first of all, I am the co-chairman of the standard, so obviously we have been working on that internally with SLB as well. Even before the standard existed, despite the fact that we had supplied a lot of valves for hydrogen services already, there were more and more questions coming from customers who wanted to get some more comfort about the suitability of the materials. So we have been testing a lot of soft materials and metallic materials already before the standard existed in order to gain that experience and knowledge. We have done some other standards as well. About technical readiness level, you can look at the different sides of it. So we have chosen to qualify our existing designs and materials that have been field proven for the last 50 plus years already. So in that case, what is different is the uses of it, because it still opens and closes, it still has a number of cycles, it still needs to seal off, etc., etc. So if that did the job for natural gas, and right now you use it for hydrogen, the TRL level is pretty high. As opposed to if you use new materials that you haven't been using before, you need to do all the qualifications in order to get to that same level. And design-wise as well, if you have a different design for hydrogen as opposed to what you have supplied in the past, it all requires a lot of designs. So Annex M, that's really for typical valves, so it doesn't go at extreme high temperatures, neither does it go very low temperatures, so it's in the sweet spot in the middle. There are different SLH levels indicated in there, so specification levels for hydrogen. And that's really up to the customer to decide, okay, to what level do I want to qualify? So we have taken the first step to qualify a little bit of the range of the valves that we intend to sell for these services. But we have not covered 100% either. We have also done it up to an SLH level of 2, for instance, because that's what we expect to come. So it is really what's a chicken and the egg situation, right? What will the customer require and specify for the requirements? But that's about where SLB is with the qualification and the readiness of the valves.
I just want to sort of follow up on that. So the selection of SLH levels. In Annex M, there's some initial language, starter questions essentially on how do you actually select it. But as operators or end users, we have to develop our own process, our own methodology on how you would actually make that choice, right? In BP, we did develop such a system. It is really a risk-based type of selection. So depending on several factors, some of them are covered in Annex M, such as pressure, temperature, size of the valve, TRL level, but other things like proximity of these valves to human population, to housing, because obviously we're talking about pipelines going through the backyards of many of us here, or shopping malls and so on. So we did develop a process to help projects to select, because at the end of the day, with each of those SLH levels comes the impact of additional testing, additional qualification, different NDE methods, and so on, and the validation itself also. Validation, I should say, isn't really that much different to a standard Annex F in 6D. It's slightly different. It's not dramatically different. So it's not something that manufacturers would struggle with, right? But one of the sort of challenges that we see from projects is, well, you qualify the valve, but you actually haven't used 100% hydrogen, right? So what do we know about its performance in 100% hydrogen? So we made that decision during the task group discussions not to go with 100% hydrogen, but go with forming gas, which is a mixture, mostly of nitrogen and just a little bit of hydrogen, and that's how we would actually get a valve qualified, right? But that's kind of the end user perspective, is how do you actually then choose what you're going to actually select for specific locations, specific units, pipeline locations, and so on, and each of those comes with additional requirements.
Yeah, I agree. And so we decide in the task group what to put inside the Annex M for 6D. I agree that hydrogen specification level increase from 1 to 4, depending on the risk. As said by Wojciech, if the pipeline is going through a city, of course the perceived risk is higher than a pipeline running in the middle of the desert, where even if there is an incident, is not affecting population or not severe damage. About Annex M versus Annex F, we decide what to do. Is longer because the duration time for testing is longer compared to Annex F, to compensate the light molecule of hydrogen compared to nitrogen. The tests we have done in SLB are with helium, where we have not used forming gas, but forming gas is also a potential opportunity. We know helium sooner or later will finish in planet Earth, so we know helium is costing a lot. So if there is the possibility to use forming gas, why not? On material, we are talking a lot about metallic material problem, but also gasket, coating, and other have to be considered. Annex M provide guidance about the qualification of, for example, soft goods that, of course, are not done at the valve manufacturer premises, but you have to rely to vendors, external laboratory, to run RGD testing on elastomer, thermoplastic. From testing we have done, we don't see any particular problem. Probably CO2 is worst in terms of damages that you can have by rapid gas decompression on elastomer. But we have also expanded our knowledge and increased the TRL on coating, because we can have coating on the valve trim, for example, EMP, electronickel plating, or we can have cladding, welding overlay to protect it against corrosion. We know that, for example, by study done in the past, the 316 stainless steel weld overlay have to be preferred against other type of material like Inconel 625, which is considered more resistant against corrosion, because there can be some penetration of hydrogen through the cladding that can attack the interface between carbon steel and 625. All the tests we have done show no problem, but these depend on the quality of the welding specification and the parameter. You know, welding is a special process. So my way to do cladding can be different from others. So we cannot speak in general. We need to do tests. And I said before, it's true that we have many hydrogen application in the past, around for several decades. But it's also true that on large infrastructure, new pipeline, famous backbone of 1,000 kilometers of infrastructure that already existing, especially on repurposing, we have to consider study and further check, in my opinion. I don't want to scare, but
no,
we need to push on hydrogen, but
it's the right thing.
okay.
Yeah.
So let me just add that if you're looking at this question from a high level, you don't really have the whole spectrum of valve design choices because there's so many of them that are just totally irrelevant for the services we're talking about here, because of the permeability, because of the sizes, the cryogenic issues, the shrinkage, and so on. So, you know, it's likely that you'd be thinking in terms of globe valves primarily, if for no other reason that, you know, liquid hydrogen lines typically are going to be small. Typically you're looking at 1 inch, you know, maybe 1/4 inch. And of course, with the vacuum insulation over it, those are real practical layout considerations for this. In general, a torque-seated valve of any type is probably better because, if you can push on it harder, maybe you can get a little bit better seal. The ball valve, I would have thought that would be a reasonably good solution also, except for the permeability of all of those soft goods and so on. So it's really not as wide open a choice as you might have thought at first glance.
Yeah, just to add, I think some of the question around technology and valves, some of it relates to scale, because as you intimated, Wojciech, there is nothing new really about hydrogen and handling hydrogen, but it tends to be smaller bore, it tends to be austenitic stainless steels. The long game with hydrogen is to expand that industry and use it domestically, industrially, in larger pipelines, transporting it up and down countries. It means an upscale in pipe size, valve size, so you're going from small, 3-4 inch valves to a 36 inch pipeline ball valve. It's a completely different question. On paper it might seem like it's the same thing, but from a design challenge and getting those valves to work effectively, it's easier said than done. It's that change in scale makes a big difference. So that's a challenge that will need to be tackled.
Excellent point.
And not outside of the cryogenic realm, we did a study on a hydrogen hub that was going to be powered by a nuclear power plant. And so to take advantage of the energy density, we were thinking about piping pressures in the vicinity of 8,000 psi or so, and that's just 500 bar. It's just beyond. It's not beyond what's normally done, but it's beyond common experience anyway. So you're not at the edge of the universe, but you're close to it.
I would like to come back to your comment about the choice of SLH. So we're here in Europe, and as far as I am aware of the European standard, there is an indication, and over there's a table, depending on the whole different kind of scenarios, it gives you kind of points of 1 to 3. And that brings you up. It's not equivalent to the SLH level, but it can help some of the end users determine what the level is. Okay, so in Annex M, we give the responsibility to the end user. In the European standard, it gives a little bit more guidance on how to get there. So in case people are not aware.
Good to know.
Just one quick one,
Please
just
go
to
ahead.
add.
Please,
So
please.
the size, that's an excellent one. Size is definitely a big one. But repurposing, right? That's something that is very different, right? So actually repurposing pipelines with valves that are 20, 30 years old, and how safe is that, right? Is it, or, does it need reworking? Yes.
We've got a whole section on repurposing, I think, but
we have repurposing is a whole other theme, right?
Yeah, but it poses a bigger question, I think, for me, because what's the end goal for hydrogen? We're all speaking about materials and how we deal with hydrogen-induced failure problems and all this, but where are we heading? Where do we want to be with hydrogen? And that seems to be large-scale industrial and domestic use, so replacing natural gas in homes and in businesses. So that tends to mean that it's just the scale of things is absolutely phenomenally bigger than what we're dealing with at the moment in terms of hydrogen. So because we already have that type of infrastructure for natural gas, it's the length and breadth of a lot of countries, large bore pipelines into smaller bore, into domestic use. There's so much sort of heavy steel, if you like, that needs to be reused. We can't discount that and sort of start saying we're going with a clean slate here. We can't afford to change out the whole network everywhere. so the repurposing is a big question, and that then poses a whole new set of questions around hydrogen, because we're talking about how to tackle problems in new product, limiting defects, reducing stresses, all these sort of things that can be incorporated up front in a design and manufacturing stage. How do you tackle those problems when the valve is already there in front of you? How do you assess that? How do you determine whether that's safe to use either with a blend of hydrogen and natural gas or hydrogen at 100%? So there's probably more questions that raises than answers, but I suppose the first thing to do is find out what we've got, because that's also a bigger issue, especially with older infrastructure, 40 plus years old. Some of the certification is not there, some of the materials are even unknown. So it's a case of finding out what we've got first before we can then determine whether we can move forward and reuse it or what has to be changed out. But maybe continue it later if the question comes up again.
We'll be coming back to repurposing, but it doesn't mean we have to cut off the conversation. Go ahead.
Yeah, I was going to add one more thing. So instead of taking the full jump from natural gas to hydrogen, we did a project in where we inject up to 20% of the hydrogen in the pipeline, and it was burned along with the natural gas as the gas companies goal to reduce, carbon emissions. So it was like a 20% injection by volume of the gas. So there's an intermediate, or the first step, I should say, of, repurposing.
I'm going to, under the theme of valve technology and somewhat touching on the last few comments that were made, I have one more question that I'm going to ask here, and that is, what are the fugitive emission requirements for hydrogen valves compared to methane standards? And what external and internal sealing technologies are applicable? And this has to almost be bifurcated or split up into the two domains, the cryogenic domain and the higher temperature domain. So I'll put that question out there, and hopefully someone has something to contribute.
So this is a good question. For sure, when we are talking about hydrogen application, also NXM introduced the request of having a fugitive emission testing on the valve itself, which for the one that are familiar with ISO 15848-1 and 15848-2, we are talking about fugitive emission testing. The -1 is type testing on a prototype valve. There is some scaling rule about coverage of valve tested compared to the rest of the production, while -2 is production testing on specific lot and percentage of the valve you are making. In terms of pollution to the environment, we can say that even a valve leak hydrogen in atmosphere, not a big deal. Methane and CO2 are, as you know, polluting more and contributing to the global warming much more than hydrogen. But for sure, hydrogen is risky, because if there is a surrounding environment that contain hydrogen around the valve and the equipment, it can be dangerous, because in case of fire, you cannot see the fire. The ignition of hydrogen is easy, and what we have done in terms of valve testing and qualification, we have done a lot of testing on different model of valve. Our coverage is more or less on CO1 performance class, BH, so class B, using helium. We had also some tests done with methane according to API standard, but for sure NXM introduced testing with helium that represent more in terms of dimension of molecular, the hydrogen. Like on traditional natural gas pipeline, is important for the operator later to do check on the valve install regularly, because the proto to qualify the valve is good. Show that the sealing arrangement on both stem, static, gland, etc. is good, but is kind of laboratory testing. The production testing, ISO 15848-2, is ensuring that the production reflects the proto, but also later to ensure that when the valve is in service and decades of application is not leaking outside, the important portion is the surveillance on what is going on outside to avoid even small leak through the leaking path to avoid potential risk. We have done also some challenging Class A testing with helium, which is the best in class, as you know. But normally the cost of introducing, especially for quarter turn and ball valve, or also linear movement rising stem ball valve, a solution that is able to meet Class EH is demanding. So this is about the risk. This is about the hydrogen specification level you want to get. Someone was driving the discussion about, oh, why not having a Class AH for all? Yeah, but the cost of the valve will increase for sure compared to what is the legacy design on natural gas. So this is to be considered. Also the cost of the equipment, because someone can say, okay, I can raise the bar up to the top, so I'm covered also for the everything below. But on economical scale, if you think about thousands of kilometers of pipeline with several compressor stations, several valves, if you raise the bar and you challenge the valve maker to stay at the very maximum level, the cost of the product will increase for sure. What about pressure? We say that the easy answer when introducing hydrogen inside the pipeline to reduce the risk, what to do? Reduce the pressure. Because by increasing the safety factor, you are reducing the stress on the part. Since we said before, hydrogen attack is stress related. By reducing the stress inside the part, you are increasing the safety factor and you are on the safe side. But when introducing hydrogen in blending or pure hydrogen inside a pipeline that previously was with the natural gas, because the density of hydrogen is lower than methane or other gases, by reducing the pressure, having less density, you are reducing the total energy amount that you are flowing inside the pipeline. So there is the pro and cons. Reduce the risk by reducing the pressure. By reducing the pressure, you cannot achieve the same amount of energy transfer through the same pipeline. This is another food for thought for the operator mainly.
Couple of comments, if I may. So first of all, you're right in saying that hydrogen is not a greenhouse gas, but it is considered as an indirect greenhouse gas. Because with hydrogen in the atmosphere, it maintains the methane longer in the atmosphere, so that methane is a greenhouse gas by itself. So that's why it's called indirect greenhouse gas, and therefore we don't want it to contribute to the warming of the planet. Then about the fugitive emission test, what some people do not realize is that the testing is within a certain temperature range. And you need to use the valve within the temperature range it is tested for, and the same amount of cycles, like you said as well, C01 or 02 or 03. So if you use a valve more frequent than it is tested against, then your validity kind of expires of the fugitive emission certification. Also, if you intervene, if there is some work done, some repair work done on a valve, and you alter either the materials or the surface finish of the meeting sealing areas, again, your fugitive emission certificate becomes invalid. Just for people to be aware of that.
Tom, do you have anything you might contribute in your field of
experience? I do. Thanks for that. I want to go back to the last question for a moment because it's kind of appropriate for what we're talking about. I'm the end user valve. I'm a specifier valves. So when I look at a valve, I have to figure out what type of valve I need. And typically we start with glow valves because they're a better sealing surface. Because one of the things we're talking about is mainly, certifying these in the beginning. And these valves may be in service for 20, 30, maybe longer years. And so you have to kind of keep that in mind on what valve you should be using. Mechanical integrity or lack of leaking either out of the valve or through the valve is obviously the most important thing. as is for methane as well. But the seats are very important, and the mechanisms that happen over time are very important. And one of the things we have not talked about is the end use application. So these are all being tested, but I've seen the valves used in different applications. For instance, in a liquid hydrogen tank, we use the valves in reverse flow direction. And the reason that's done is so that the pressure on the downstream side is not pushing on the packing consistently. So that's very important to understand the end use application as well. So not only the type of valve, but how it's being used. Another, for instance, is on a liquid hydrogen fill line. You tend to get some moisture in the line, which can be a problem for the valve. Additionally, you have to consider maybe fire sources. You know, if you have a hydrogen leak that ignites, it could heat up the valve, which could melt the seat. And we've had that happen before on mainly on gasketed valves that are on the flanges. And it melts the flange and goes from a small leak to a large leak. So those are all important things you have to look at when you're using a valve and an end use. And then the last one is the mechanical integrity of the leaks indoors is very important, because the hydrogen normally burns in a fire, but it can also explode. So it's a little different than methane, although it explodes as well. Hydrogen is easier. So trapped, congested hydrogen causes problems. So that all has to be considered in the type of valve being used, the packing being used when someone is choosing a valve. So those are kind of my points. To start with, all the testing's done well, and then how does that flow downstream later? Thank you.
Thank you, Tom. Are there any other insights regarding fugitive emissions? Or okay.
No, about fugitive emissions for a liquid hydrogen valve, I agree with Tom that the globe valve probably is the more used valve with bell of seal on the stem that guarantee the sealing, perfectly sealing for a lot of thousand cycles. The other point in this type of valve is the leakage through the upper part of the valve, the bonnet, that is very far from the body. The body is the part of where the liquid hydrogen stay practically always, because in the extension you can find always 100% of gas. This is one of the points that we can discuss later, because the design of the extension of this valve is one of the most important and critical part, due to the fact that if the extension is too short, the temperature on the upper part, on the bonnet, is too low, and it's necessary to study a different sealing system. But this is not a problem. The real problem is that it is generated by a lot of heat loss that come in, and you have a lot of evaporation of the hydrogen, liquid hydrogen, due to this. So the most important thing is to design the extension in proper way, and if you design the extension in proper way, in the upper part of the extension, the temperature is ambient temperature. In this case, this type of valve, generally speaking, also the customer has to use an O-ring, rubber O-ring as a first one, and due to the fact that is hydrogen, as a secondary seal we use a graphite for the fail-safe. So it's very simple. For the stem, if the valve is a globe, you have no problem about the fugitive emission, because there is the bell of seal. In case of quater-turn valve, okay, the bell of seal is not possible to use, but it's possible to use some packing that is not too much different to respect the standard valve at ambient temperature, due to the fact that in that area, in theory, it is always ambient temperature, okay? And the fugitive emission as per ISO is the standard requisition to verify the sealing system.
Thank you.
I would add to that, that's a great point. And I'd add to that, when you have the sealing system start leaking with a cryogen, as it gets colder, the leaks get worse, to the point, because everything is contracting in the valve and maybe at different points. So typically we might have no leaks when we start up a system at night. The next morning we come back, we might have a pretty bad leak that has gotten worse and worse over time. So it's important to understand that a small leak can turn into a large leak, and to understand how that's managed. Thank you.
Thanks, Tom. Moving on. The next thing we have is on corrosion and environmental compatibility. How do impurities, we talked a little bit about this before, how do impurities from different hydrogen sources, the colors of hydrogen, etc., affect piping corrosion, and what monitoring strategies should be employed? Are we covering similar ground? Are we being redundant, or is this something?
It's on. Yeah? Okay. So, again, impurities depend on the production route and of the hydrogen, of course, the colors. And those impurities will define the corrosion chemistry in pipelines, okay? So, for instance, if gray hydrogen carries typically the CO, CO2, traces of sulfide, a blue hydrogen, similar impurities but reduced through the, for instance, carbon capture, and depending on also on the process efficiency. Green hydrogen. Green hydrogen is the cleanest in terms of carbon, but may contain traces of oxygen and moisture. So all those impurities create localized corrosion. This is the issue. So there is a localized corrosions, and then there is hydrogen that impact. Here where we meet corrosion with hydrogen embrittlement. And you can guess what is going to happen under pressure and cyclic conditions. So we initiated the crack is faster. With the hydrogen, we further accelerates the crack growth and propagation.
Yeah, so I would like to add something. I read an interesting article about contamination of hydrogen, and I think this had to be shared. Please. There are some impurities that are acting like inhibitor. There are some other impurities of hydrogen acting as accelerator of cracking. I was surprised when reading such article. There are still some contradicting opinion about that, so further study have to be done. But for example, oxygen or SO2 is acting as an inhibitor. I was surprised, but normally oxygen is corroding because it's while, for example, H2S or CO2, of course, are accelerating the damages. When talking about blending or hydrogen, if we imagine a pipeline that starts from the source of hydrogen that can be green, I'm thinking about new pipeline starting from offshore wind farm, solar panel, electrolyzer generating hydrogen. For sure, at the beginning will be 100% hydrogen, more or less, no impurity. But we need to think about the distribution, and also when this new pipeline will get inside the existing network somewhere, or if not used immediately, someone can think about storage in the cavern. We are receiving many inquiries for that. When putting the hydrogen in, coming from green source, for sure is pure, but when going inside the cavern we consider empty because the reservoir is exhausted. But in reality, there are some other factors to be considered. There can be some H2S, CO2, liquid, impurity, other different impurity, like sand that can come out, and also bacterial growth in the cavern. Okay. So everything going inside the cavern as pure. When you need the hydrogen, you are opening the valve, you are releasing hydrogen, is not more 100%. Is mixed. Of course, more you use the cavern and more you try to clean, but it's not a real cleaning. It's dilution of the contamination you have. So very important to understand this. And also, as said, hydrogen can be green, violet, blue. Okay. So contamination is different. Some contamination act as an inhibitor, try to reduce the attack and the propagation of crack, because they are, it seems from study done, they are forming a sort of ductility area in the sharp edge of the void that do not allow propagation. In some other cases, like H2S, we know H2S is causing the similar type of attack like hydrogen in those stress cracking.
I just want to add something there.
Please.
Here where there is unpredictable corrosion. You start with your question, okay? Why? I just give you one because we are maybe have a time to discuss, okay?
Please.
Because hydrogen is unpredictable. Because we don't have enough long-term data. We are not confident. This is the point. With a high temperature hydrogen, we do have so many decades of experience. And on top of that, we learn from our failures with the valves or equipment. This is why uncertainty that make the hydrogen, not only because of its physical properties, but because it's unique and we don't have enough experience. We are learning as we go.
Yeah.
This is why make it a little bit unpredictable.
Thank you.
There's also the lack of, I guess, consistency between, even within BP with different refineries, what choices we made or our suppliers of hydrogen into refinery, what equipment they have selected, what specifications were used. That was one of the good outcomes out of 6D, is that we could be consistent now. We could actually consistently call something, this is actually a valve for hydrogen, whether it's very basic, right, to much more complex. At least there's some consistency. I found, because we have pipelines, we have ball valves, we have gate valves, we have valves that were repurposed or pipelines. It was all kinds of services, and then suddenly switched over to hydrogen. It's not unusual that you walk around at night and you see glowing around the stem packing. If you don't see that during the day, they walk around actually with a broom, right? If it starts to burn, that's their method of detection, right? So it's we talk about future missions. This is much more than ppms, right?
Yeah, much more, right. I have, I think, a related question, and it kind of touches on what you just mentioned about oxygen, and that was, what are the specific concerns regarding oxygen contamination? In your case, you just talked about maybe one of the benefits, but oxygen, what are the concerns regarding oxygen contamination in hydrogen systems, and how do oxygen ingress and removal strategies differ between gaseous and liquid hydrogen applications?
Yeah, as said, there are several studies partially contradicting one to each other, so I think more research to be done. But in general, what I see is that oxygen in some cases is considered an inhibitor to the propagation of cracking. Even oxygen is another element that causes corrosion. The study has been done, and also another interesting publication is about repurposing of pipeline, which is connected also to this. There is a 91 pages study that was concluded, if I'm not wrong, 2021, about what we have to do on existing infrastructure pipeline. The study, I think, was around 28,000 kilometers of pipeline, and was done by IOGP for the European end user. And what I see is that 70% of the existing pipeline was considered safe, while for the very old pipeline that are in action since decades, there is not supporting documentation, because at the time was not digital. We're speaking about 80s or something like this, and we have to be careful. The pipeline considered safe are exactly with material we talked before, so low-grade carbon steel, and this study involved, I said, thousand and thousand of kilometers of pipeline, but we have to remember that the pipeline is not alone. There is equipment, compressor, station, valves, fitting, flanges. So I don't know if that study was also including eventual revamping of some of the interconnection, like flanges, bolting, gasket, and so on and so forth. But as said, that study is confirming that we can be on the safe side for majority of 70%.
Thank you. I just want to add one thing. The oxygen ingress in gas and liquid hydrogen is different. Okay. In terms of, we talked about the oxidation. Okay. But I think in gas, the risk is the safety hazard, flammability interactions. Because in gas hydrogen, the oxygen can mix with the gas. However, in a liquid hydrogen, oxygen can accumulate and condensate and accumulate. It's completely different behavior, by the way. Okay, and the risk will create this accumulation of oxygen in a local regions can create hot pockets for ignition.
Yes.
Therefore, it's a critical to oxygen. I mean, safety.
I was going to ask Tom for his input on this. I think this is a situation or an issue that you've confronted many times. Am I correct?
Yeah, many times. So pipelines, and both liquid and gas, have to be purged. The purge gas with liquid hydrogen lines is different, but regardless, we're trying to get rid of any oxygen. And consideration is anything above 1% is a problem. Now, normally, hydrogen will show up at parts per million oxygen. There's very little in there. Obviously, the air is another source of oxygen we need to purge out of the system. So purging is a common experience with both liquid and gas, and liquid hydrogen has other issues as well, because what happens when you have a liquid hydrogen line you've filled, when you're done filling it, the inside of the line is still cold and it cryopumps air in. And that air has moisture in it, and the moisture is actually a bigger problem because the purging of the oxygen is done at warmer temperatures where the water is very difficult to get out as liquid water. So in fill lines, you can end up with some liquid water in the line that could affect the valve operations by freezing the next fill. So it's kind of important to follow good purging procedures on hydrogen. And when we purge, no more than 1% oxygen when we're done. For liquid lines, it's less. I think that was an excellent point on oxygen solidifying in hydrogen can create some very dangerous situations. Thank you.
Thanks, Tom. I'm going to move on because the time is marching on, actually at a pretty good clip right now, and I realize we got to get through all the themes. The next theme is testing, qualification, and commissioning. And there are several questions here. I guess I'll start with the top one here is, what is the current state of qualification testing for non-cryogenic hydrogen valves under API 60 Annex M and other standards? We touched on it a little bit, but maybe we could have a re-summary of that and just get a clear summary picture of that.
I can't speak for all valve manufacturers, obviously, so I think that's a question that needs to turn around everywhere. I guess there are some manufacturers that take into account different standards. Annex M, I think that's the only available current. Well, hang on. So there is the DVGWZP4110. That's a standard that has been existing for many, many years already. I've spoken with one of the task group members. It appears that standard would be in terms of revision because it was developed years ago, not with the knowledge that we currently have. So, and apparently they would like to seek for representing the Annex M, API 60 Annex M requirements. There's also the equivalent ISO standard 14131, if I'm not wrong, equivalent API 66D standard that reflects the same requirements as well. So I think we're recovering those requirements. Now, a customer can select to put those requirements in his specifications or not, right? It's not mandatory. It's not a regulation or so. So it's really a question that we need to ask to the different valve suppliers. Again, what I mentioned earlier at SLB, we have been proactive by validating testing a lot of valves already. But even there, we're not covering all the materials design because you have a top end tree, you have a side end tree, you have a fully welded, and you have different materials.
Right.
It requires really a lot of testing.
Correct. Yeah, especially when you're talking about overall qualification testing, it's a broad spectrum.
Correct. Now, I guess most manufacturers, they have already some of the qualification already, like fugitive emission testing. So that's part of the requirements.
That is, yeah.
And same, maybe some materials already tested already, although that's a new requirement. Yes, but there's a lot of testing to be done.
Yeah, even if I can add something about scaling. So everyone dealing with ISO know the scaling role. If you test a 100 millimeter stem, you are covered from 50 to double, so 200 millimeter, same pressure class and below. So by doing one proto, you can cover a lot inside in terms of size and class. While for Annex F and Annex M, if you follow strictly the rule of scaling, you have to do a lot of tests to cover, especially for valve makers that are making from 1 inches to 64 inches, all pressure classes from very low to very high.
Yeah,
so
I calculated from 3 inch up to 56 inch, class 150 up to class 1500. It's about 9 valves for the same design, same materials, right?
Yeah.
Right.
Yeah.
Then, if your offering is also including variances like, I don't know, FKM, HMBR, superfluorostomer or so, the number explode. So...
Yeah, it's a challenge, definitely.
It's a challenge, yes.
And then again, I would like to repeat, it's important for valve manufacturers to understand what is the expectations of the end users, right? So, because, we want to fit that. We can do a lot of testing. There's a lot of cost involved, a lot of time involved, but it doesn't match the operator's requirements. We're doing it for nothing. So that exchange of information is very important for valve manufacturers.
Yeah, totally agree.
Just from the end user perspective, on very few projects these days, new projects, what we find is that effectively we have to go with qualifications every single time, right? So even though we go to the market, to manufacturers that are well established, we find that every single design basically has to be validated, right? Some, and this is BP, but some other end users have validated their designs before Annex M, and they have their own validation process, and they're happy with that. So there may be some existing designs that have been qualified or validated, but they've been paid for, they've been sort of protected by the other end users. So you can't just say, okay, well, give me the same design. We're going to have to pay again, yeah.
In a case like that, where you expect a high degree of qualification, how do you treat and interpret the extension rules or the extension validation? What guidelines or system do you use for that?
We follow the 6D.
6D, okay.
Yeah. So there's some scaling as you said, right?
Okay.
But effectively, the range of valves on these projects is quite wide. So you end up with very large valves, 36 pipeline valves. You end up with a lot of 4-inch and 2-inch and so on as well. So you can't really do 1 or 2 designs. You basically are stuck doing almost every design. Yeah.
Okay.
Maybe in the future when we have more of these, we can take advantage.
Be more confident that one package can apply to a neighboring package.
Yes.
Yeah. Related to that, though, then is another question, and that is, what is the current state of qualification testing for cryogenic hydrogen valves under MSS SP 166 and other standards? That's a bit of a softball for me because I just finished working on that with the team at MSS and other subject matter experts, some of whom are here. And I won't answer my own question because I'm going to be making a presentation on MSS SP 166 soon. Might sound like a sales pitch, but it isn't. It's more that there's a distinction here between the non-cryogenic and the cryogenic, and There have been specific needs to the cryogenic case that haven't been met until now. And so this question, which I put out to the group, is, what are the qualification methods or testing that have been in use, and to what extent, let's say, does MSS actually impact that? Go ahead. I threw you a soft one.
For us, we have developed together the Italian Institute of Physics and Nuclear office the special qualification test method. We use a cryo cooler inside in a tank where we obtain the vacuum up to 1 by 10 by minus 8, okay, and we use more or less the same idea of the quantum computer, okay. So we start with the cryo cooler we move the cool from the cryo cooler flat to the valve, okay. The valve, when the valve arrive, all the body of the valve arrive at minus 253, 52, 20 Kelvin. We start the test with the helium, okay. This is take a lot of time to arrive at the temperature. It's not very quickly. For example, 6 inches valve, that is the maximum that we can test in this system. We need 5 days and 5 nights to arrive at the temperature. And also the test is not a test that you can carry it out in few hours, because you have to imagine that you have to put inside the helium at ambient temperature. So each 3 or 4 stroke, you have to stop maybe some hours to reduce the temperature at the temperature of test temperature. So that require more or less 10 days, 12 days to finalize the test. The test, it has been done in line with the MSS 166, 200 cycles, and it is the results are quite good. The valve was a globe valve, okay. At the moment, we are developing the new design of some ball valves, and the 2 inches is under test at the moment. Always at 20 Kelvin temperature. This is one of the methods out of 166. The other 3 methods.
There are 3 methods total. Yes. There's immersion.
That immersion is split into parts for the bigger valve and the smaller valve.
There are 2 variants of immersion. That's right.
Exactly. For the bigger valve, it's not possible to use the similar test that you can see in the other specification, like 28921.1 or 2, or the MSS 134, because to use liquid helium for the bigger valve, the cost of the test should be very high. For the bigger valve, we have introduced a different test method that is always immersion, but a little bit different. So we have to build practically around the valve like a jacket where you can fill in of hydrogen, liquid hydrogen or liquid helium, but the quantity is obviously much less than immersion test. And you have less boil off. That is very important. And the last one is a method that it has been introduced, suggested by the Japanese company.
That's a flow-through method.
Flow-through method, yes. Yeah. The temperature that is acceptable by the specification is from minus 243, if I remember correct, 43 or up to plus 255, not more, because at 259, minus 255. Minus 255, because at minus 259, in theory, the hydrogen change of state should be solid.
It's subcritical.
Yes.
Tom, I was interested in your perspective, because you were part of that team as well that put the standard together, and you had a historical perspective on testing for cryogenic purposes, and I'd just like to hear what you have to say about it, and if you have any other comments regarding 166 as well.
cryogenic testing on valves is difficult. You know, like I said, I've done cryogenic testing at Cape Canaveral, and it is difficult to keep the liquid in the system, even liquid nitrogen. Originally, the safety team at NASA wanted to use liquid helium, but there's not enough liquid helium in the world to test their pipeline, so that was negated. But the expansion contraction is important, and how the valves open and close is very important. So that was kind of my critical item to make sure these things work correctly. The testing was interesting to see from my side because I'm always looking at the operation, and I heard the manufacturer's issues with it and understood them. But liquid nitrogen is the way to go, is the best way to go with it, and keeping it liquid is not simple. So it's a difficult process, and it like I heard earlier, a lot of days of testing needs a lot of liquid nitrogen. So thank you.
Thanks, Tom. I'll move on. Next theme is pipeline repurposing and conversion. It's a big subject. What are the key technical challenges and assessment procedures for repurposing natural gas pipelines for hydrogen service, and what percentage of existing infrastructure is considered suitable? We've heard some answers to those questions, but... Yeah. Yeah, sorry. Maybe I should ask another question, but let's answer that question. I'll repeat it. What are the key technical challenges and assessment procedures for repurposing natural gas pipelines for hydrogen service, and what percentage of existing infrastructure is considered suitable? And I'm going to skip to another question if we don't spend a lot of time on this one. Is there anything else we want to add to that?
So let me comment on that real quick. There's two areas. Obviously, the pipeline is one of them. The leakage on the pipeline, it's all mechanical integrity, right? What's going to happen over time with the pipeline? Will it leak more hydrogen and create a problem? Both methane and hydrogen are flammable. The difference is the hydrogen doesn't have any odor with it. And then the next piece of it is what happens inside the house, right? The end-use appliances, can they handle what percentage hydrogen? So it's more than just the pipeline. This is a big question. It's being, to date, 20% is considered safe. It's more towards the properties of methane than it is hydrogen. As you increase the hydrogen, the properties go towards hydrogen. It becomes less safe and more issues associated with it. And again, the biggest thing is mechanical integrity. So it's not just the valves working on-off. It's the pipeline connections, the threaded joints. Those type of things, besides the pressure rating and the temperature ratings, are very, very important. Thank you.
Thanks, Tom. Please.
Yeah, just to add, it's a huge question to be asked. I suppose one of the things to consider as well, just as a higher level thing, is the reason why we're wanting to use hydrogen, or the reason why it's sort of looking at being big. It's because it's less carbon emissions. It burns clean, obviously. So that's the whole thing, is to reduce carbon emissions. If you have to rip out entire pipelines and valves and things like that, there's a huge carbon emissions question to be asked about that as well, because steel manufacturing, for one, and especially in the sizes that we're looking at, to recover that type of carbon that you would emit just in the production of the tons of steel that you would need, it would take years to pay that back as well. So you're sort of defeating the object a little bit. So for me, repurposing has to be part of the answer. We have to try and use as much of the infrastructure, as much of the equipment as we can. Which is probably not ideal to a lot of the valve OEMs in the room, but so the question is, what can you reuse? I think pipelines are probably, the actual pipes themselves are probably easy to assess and answer, because as we've already discussed, there's less geometrical changes, less sharp corners, stress raisers. When you start looking at valves, all those things exist in the valve, and they're the things that you would design out of a valve if you were creating one from scratch. They're in existence. So how do you get around that? We've discussed reducing pressures, maybe an answer, but that brings its own problems. But the other question, as I maybe mentioned earlier, is the availability of the data. Because a lot of the equipment that we're talking about repurposing is 30, 40 years old. And the certification, any valve documentation sometimes is just non-existent. So without a thorough investigation, you'll not find out what materials a valve is made of, what condition it was bought in. All these things then start to become a problem. So no doubt there will be many valves and bits of pipeline equipment that will need to be replaced because there's just not enough background data on the equipment that's there. But there will be some, especially the newer installed equipment, that you've got decent amount of data on, and there's no reason that you can't do a fairly in-depth assessment on it and validate it for future use on hydrogen. But there is a big piece of work to actually get that data and do the assessment.
The assessment, yeah.
If I can add something, Gil?
Pardon, yeah, please go ahead.
No, from VALVEmaker side, we are receiving some questionnaire survey from final client utilizing our valve in the pipeline, because when introducing a hydrogen, the question come in like about valve we have from you installed in the 70s or the 80s. I'm safe to introduce blending of hydrogen up to 5%? Question, difficult question, $1 million question, because I don't know the story of the valve, the maintenance. When retrieving still the old document, paper made, okay, good. The material at that time used is now, I think, obsoleted. At the time we made the valve, there was not existing fugitive emission standard, there was not a rapid gas decompression, there was no NORSOG, there was not such accuracy we have today on qualifying the material. So for us, VALVEmaker is a difficult question to answer at the end. Yeah. Even someone can go and do an assessment or maybe improve the packing, the internal of the valve without a strip down and a physical look at the part. It's difficult to predict the level of corrosion, pitting, maybe some other stuff occurred where, and so on. So repurposing of pipeline, good, to save carbon. Otherwise, reinstalling everything new will be easier in terms of safety, but the cost a lot. But also valve, when reusing a valve, we have to do some survey, and we have to share knowledge. We have prepared a sort of guideline internally to guide the final user and client how to do. There is a flow chart that is suggesting what to do based on 100% hydrogen or blending at the beginning, and based first of all about maintenance done so far, track record about what the valve has experience, and also service track record.
Yeah, I was going to say, I think that hearing what we're dealing with in repurposing, a fitness for service type of discipline needs to be evolved. There are precursors to this that we could learn from, but it seems that it's essentially an emerging field, and it needs deeper insight to be able to come up with an appropriately applied fitness for service regime that looks at repurposing pipelines. We don't have the answer for that, but we have to start exploring the methodology to develop it over time. So that's not an answer.
Yeah, this has already been done in the UK. They've had, I think, several years operating with hydrogen in the methane pipeline. So it's being done. It's being tested by the natural gas companies, and so they are looking at that already, and has been looked at, and it's starting to be introduced into the standards. I'm on the NFPA2 committee, and they've actually changed the percentage hydrogen that it covers because of the blending of hydrogen to the natural gas lines.
That's great to know. Thank you. Okay, I'm going to move on to the last two themes. I'll move it along a little faster because we're coming to the end. There are several questions, but I'm going to take one that I kind of lumps them together. How do the fluid flow characteristics of hydrogen differ from natural gas in pipeline systems? And what are the implications for allowable velocity, compressor selection, pressure drop, flow metering, and valve sizing?
So in general, it's considered, and I'm sure Tom will input on this as well, but increased velocity, there's a comparison of mass density and velocity. And, typical velocities, you're looking at 3 meters per second. And based upon the comparison of mass density and velocity, you can increase that to 10 or 12 meters per second in the pipeline. How does that affect the wear on the valve seats? I'll let the valve manufacturers answer that, but so it is generally accepted that the velocity, allowed velocity in the pipelines can increase. On the liquid hydrogen side, for sure, the process that pipeline is serving has to be evaluated. You know, how much heat loss is going to be allowed, you know, with adding mechanical energy with the increased, you know, turbulence and such. But in general, the velocities can be vastly increased. And Tom, do you have any input on that? I'm gonna play Gil here for a second.
Go ahead.
Yeah, I do. We've first of all, liquid and methane will never be put together because the methane will go solid.
Oh,
It's,
yes.
LNG's, you know, minus 250 Fahrenheit. Hydrogen's minus 423. Sorry, I'm not using centigrade, so I apologize for that. But the LNG, the natural gas would be solid. So the only blending is going to be in the gas lines. And hydrogen has less pressure drop. I don't really deal with velocities, so you guys probably know that better than I do. I deal with pressure drop. And when the pressure drop is minor, and that's normally where you design, is where the pressure drop is small, we don't really worry about the velocities. And then what happens is the velocities come up and become a problem, then the pressure drop's too high for the pipeline anyway, and you have the wrong size equipment. So it's not as velocity issue with hydrogen, not like oxygen. So oxygen velocity is a big deal because it'll ignite the pipeline. Where hydrogen, it's mainly pressure drop in the operation, you know, and when you get too high enough pressure drops, the velocities are high, but you can't really use the pipeline. So that's the way I'll answer that. That's a really good question. Thank you.
Thank you both. Moving on to, I guess, the second to last theme, in a sense. That's really the last theme. On maintenance, repair, and inspection, have appropriate NDE techniques been identified and validated for hydrogen surface? And is the industry aligned on a comprehensive risk assessment framework for selecting suitable SLH levels? Are we good there?
Yeah, I'm not aware of operating conditions, so what the requirements over there are. I think that's more important for the pipeline than the valve itself, probably. But in Annex N, we have specified for standard, so non-H2 requirement. It is only required for the PUP, to the end connection welding to have full NDE, and the rest is kind of not mandatory. For hydrogen, we have specified that for all pressure containing welds, there has to be volumetric NDE. And surface as well, so like the dye-penetrant or MPI. So there is an increased NDE requirement in API 6D for the welds, and that's independent of the SLH level. Then the SLH level also refers to a QSL level, so quality requirements, in which you may have some additional requirements in terms of quality for the casting, for the forgings and other materials.
Thank you. Any other comments to that question? Sounds like we ended on an easy.
Yeah, I'll comment on that real quick.
Go ahead.
I'm more interested in, you know, they're interested in testing and the NDE around testing. We're interested in the NDE around, or the testing and checking for leaks downstream. And there's a number of different methods used. But one of the ones that use probably right on the joints, there's some detect tape that's used that changes color from tan to black. And so you can see leaks besides regular detection of hydrogen or flame sensors. So that's and then obviously during commissioning, we're doing other things too. So during a commissioning of a new system, we use pressure checking and maybe helium mass spec on some real sensitive stuff on the pipeline. But generally speaking, I'm after the fact, after the manufacturer. So thank you.
Thanks very much, Tom. That brings us to the end of the 8 main themes that we had. I wanted to just open up the floor to any questions. There weren't any during the discussion. I don't know if we just managed to answer all your questions before you had a chance to ask them, but please, go ahead.
Hi, thanks. I work for a manufacturer of valve maintenance products, so Valtex and Seal Weld. I was wondering, so in Canada, I went to a hydrogen convention a few weeks ago, and they mentioned that they've made the decision in Canada to have 20% hydrogen in all of their pipelines because of all the reasons that we mentioned here. For 100% hydrogen, do you think that there's a space for valve maintenance products like lubricants and sealants, or do you see a push towards just valves without, like globe valves, for instance, that won't need any maintenance products?
So part of question coming in at the valve maker on survey related to hydrogen. One of the questions is about lubricant type of grease to be used. We identified one or few best candidates to replace the standard grease we are using when the application is methane. That through the testing and the laboratory test that they have done, it seems to be good with hydrogen. The other application where we are for sure removing any type of lubricant is oxygen, because it's a contaminant, the oil and the water portion of the lubricant. So for oxygen service, we are not suggesting any type of lubricant, but for hydrogen service valve, the end user want to have the possibility to inject lubricant or sealant, or in any case other flushing fluid to clean the surface of the sealing area, the critical area, and also to stop eventual leakage in case of need. Not only for the stem, which is the most, how to say, is a dynamic sealing, so more affected to eventual leak, but also on the seat to ball or seat to gate contact area, to eventually really have a tight shut off after several times in service. But some lubricant have been already developed in this regard. Not sure if coming from automotive, because automotive, we have now batteries, full electric car, but also hydrogen is a source of energy for transportation. I think that type of grease has been developed for small part for engine, and then tested also for large component, but there is some product available.
So generally speaking, lubricants are not injected into smaller lines purposefully, and that's in the hydrogen industry. The end use application may or may not like that lubricant, so the purity of hydrogen is maintained. And as was said just a few minutes ago, for fuel cells, it's a no-no. You can't be injecting any sort of oil in there. The purity requirements for a fuel cell are extreme. I mean, much more. And liquid hydrogen is really the only one that meets the requirement. Gaseous hydrogen they live with, but they're concerned about the life of the fuel cell. So generally speaking, for smaller non-pipeline systems, lubricants are a no-no and not used. So thank you.
Just wanted to ask, because one of the discussions in 6D was lubricated plug valves, right? Because obviously they rely on the lubricant, and I know we don't have any, do we? Any plug valve manufacturers here, or maybe in the audience, but they apparently did develop specific lubricants for hydrogen. Now, what service or what applications they're in, where you would actually select a plug valve? You talked about, you know, how this selection can vary between a gate valve, ball valve, butterfly valve is a big topic as well. But there is some lubricants apparently that have been developed. In terms of sort of intervention, right? Of course, to operators that's very interesting, right? Is, you know, some years into the service, do I have any choice? Can I actually fix, right, or help with isolation if I don't get that isolation after some time, whether it's because of impurities, not the oxygen impurities, but because of the sand or debris or whatever it is, just like any other valve would suffer from. To my knowledge, I don't think there's any products yet, but question to the audience as well if you know of any. But it is something that we would be very much interested in.
Thank you.
Sorry, just quickly, I think there'll definitely be a need for sealants, particularly on like ball to seat, because they inevitably leak after a certain time, especially on hydrogen. But the other question for me is maybe needs asking is the fittings. The injection fittings are traditionally just a single thread, and on hydrogen service that's probably going to be frowned upon, or want to eliminate just single threads. So there may be a need for a hydrogen injection fitting with additional seals or different technology. So that for me would be the area that we'll be looking at.
We have time for one more question, if there is one from the floor. Please.
Thank you. That was, I think, an interesting conversation in a lot of areas. One diversion, if you like, that I had that wasn't particularly well covered for me was there was a lot of discussion about pipeline materials and appropriate use and failure mechanisms, etc. Most valve manufacturers also have a challenge of high-strength materials, particularly for components like trim and stems. What's the view as the most appropriate high-strength materials for hydrogen applications?
For trim and stems?
Yeah, stems in particular, I guess.
In particular? Okay. Valve manufacturers.
So as said before, the 316 stainless steel is the best material, or 316L, to be used in general for trim, ball and seat, but sometimes the stem suffer must versus MAOT verification. Means that 6D always is asked to verify the maximum output input torque compared to the maximum torque that the stem have to withstand. And 316 stainless steel on stem is rarely used due to that concern. So as said before, alternative to 316 stainless steel could be nitronic 50, but the suggestion is to use the low grade, not the high strength. Yeah, because the high strength can have an issue on NACE. We are not suggesting to use a duplex material on hydrogen. Then some client can accept alternative material, for sure the very exotic one like alloy, Inconel, or so on. But the question is very good, because 316 stainless steel on stem sometimes is not enough, or could be enough only if you increase drastically the dimension of the stem. And okay, you can do that in some cases, but by enlarging dimension on the stem, you are increasing also the potential leak quantity.
And actuation.
Yeah, and also the actuation, depending on type of valve, for sure. Yeah. Someone would like to add something?
I've got a question, if I could ask it.
Okay, last one.
So it was touched on that different locations, different countries are starting to introduce hydrogen into their national gas transmission. How does that change throughout the world based on regions like UK, Europe, America, Canada, South America, and then Australasia as well?
Are you referring to repurposing specifically, or in just
well, just the overall strategy, either repurposing or building new. What areas are being looked at geographically?
I don't know.
Is there any trends?
Do you have any insight on that?
So I can't really quote the actual organization, but there's some work that was done in Hawaii actually. So there's a whole network that uses hydrogen up to 100%. Right, or there's quite a bit of evidence and history, and you can probably find it. It's publicly known. It's just I can't remember now. There's some work also done in Canada, right, in Calgary, I think, and in Australia as well. So the same organization that was doing work in Calgary is starting this work in Australia as well. And these are publicly funded sort of installations where they test. I think someone said it's not just about the pipeline, but it's all the way up to your stove, right? what happens with the network distribution that is not just pipelines, right, but actually local distribution to houses and so on. So there's been that's what I'm aware of, right, and it's years of it, not just sort of the last 10 years.
And the trend is to try and use the existing pipelines. I mean, as was said earlier, I mean, there's a lot of money that's been spent on those pipelines. So to put a new pipeline in is not really cost effective. So they're trying to determine what they have to do to the existing pipeline to use it. And the appliances, as was said earlier. So there's a lot of testing going on for the appliances to see what can happen with that. And the concern at 100% hydrogen is the ability to understand when you have a leak. Natural gas, we're kind of all used to. They use methylmercaptan to odorize it. Typically with the hydrogen, it's not odorized, so they would have to odorize the gases. And they could, I think, within the pipeline, odorize that as well. So when they mix it at 20%, it's already odorized, and that makes it easier as well to detect it if there's a leak in a house or et cetera. Thank you.
Thanks, Tom. That concludes our roundtable and the Q&A. Thank you all very much. There are going to be 2 presentations coming up shortly. Is Mr. Willicke here? Mr. Willicke, okay, very good. I think we'll give ourselves a 5-minute break and we'll reconvene, let's say at, call it 10:10. So that's a little more than a 5-minute break, just to allow us to transition. And then we'll continue with a couple of presentations. One on some interesting information regarding metallurgical issues in hydrogen and failure mechanisms. And then I will conclude with a presentation on qualification testing of liquid hydrogen valves. Thank you very much. To just wrap up, thank you all very, very much. Excellent, very interesting. I learned a lot, even though we've covered these subjects over the last few months. I continue to learn from you all. Thank you all very much for your participation and your insights and your experience. Grazie. Thank you very much. I hope we